Hello everyone and welcome back to my channel and welcome to Science Sunday. Today we're talking about gravity, and yes, I did my makeup way too long and way too much, but I like it. I have no regrets whatsoever. As you can see, I have a planet and stars and I think it looks beautiful. I did a similar look a few months ago, but I like to think I upped up my game. And today we're talking, as I said, about gravity. I intended on... As I said in last week's video, I wanted to debunk the Einstein sucks series from Antiglobe. But first of all, after I uploaded my video, he renamed all of the videos. I looked a bit more into his videos about gravity, and I have to admit he really had some actual efforts in thinking about gravity and what it means actually. And so I decided I won't do a debunk with making fun of him and look how stupid you are, because even though he came to the wrong conclusion and had pretty wrong assumptions from the beginning, he actually looked into gravity and into the whole theory and had actual ideas, and I want to respect that. Credit where credit is due. That's not what every flat earther does. So I wanted to use this video to just educate him and other people on gravity and basically just answer some questions and correct some assumptions.
So, what's going on with the bowling ball and the feather falling at the exact same rate? We're claiming that the Earth has gravity due to its mass. It's attracting the bowling ball and the feather. They also have mass. So mass attracts mass. The only problem is there's more mass in the bowling ball than there is the feather. So there's more force in the bowling ball than there is the feather.
So this is a valid question, I think, because there are people out there that aren't flat earthers that are kind of put off by the idea that things, regardless of their weight, fall at the same rate in a vacuum, like the bowling ball, as he said, and the feather. He is also right that the bowling ball has more mass and therefore there's a bigger gravitational pull. But that doesn't result in a different acceleration in the free fall. The effect of the bigger gravitational pull on that more mass is what we call weight. So things that have more mass are heavier. That is the effect of the higher gravitational pull. But regardless of the mass of the object, if a feather or a big ass truck, everything falls with the same acceleration towards Earth's center of mass with 9.8 meters per second squared. That is a concept that is hard to grasp for some people, because in our world, when we observe a feather and a bowling ball, we'd say, yeah, the feather falls more slowly because it's lighter. But it's actually not because it's lighter, it is because it has a higher air resistance, because the atmosphere gets pulled down also by gravity as everything else, and all of the air molecules on or near the surface of Earth are basically in the way of the feather falling. So the feather bumps onto those molecules and falls therefore slower. But that has nothing to do with the gravitational pull on the feather, but with just air resistance. That's why we always refer to the free fall in a vacuum.
And you would think dropping them in the gravitational field of the Earth with their own gravitational field, that there would be a difference.
So technically you are not wrong here. There is a teeny tiny difference between the bowling ball and the feather. but it is almost non-detectable because it's so tiny. When you compare the gravitational field of a feather and a bowling ball to Earth, it's basically negligible because it's just a fraction of the gravitational pull Earth has. But when you would use, for example, the moon compared to Earth, then there is a noticeable difference because they both have a pretty fairly big gravitational fields around them. Technically, you are right. The gravitational field of the bowling ball is stronger than the one of the feather. But in the scenarios we use in our everyday life, when we talk about the gravitational pull, we always only refer to the pull of Earth to an object, and we won't take into account that object's gravitational pull on Earth, because that does exist. But you are on the right track here.
You're not changing anything. You're just making everything larger. So a bigger vacuum chamber, bigger bowling ball, bigger feathers, bigger Earth. But I know if the bowling ball is the size of the Earth, or bigger, and the Earth is much bigger, vacuum chamber is much bigger, everything's humongous, right? And you're going to agree that, an Earth compared to an Earth-sized feather, like an Earth-sized bowling ball compared to an Earth-sized feather, the Earth-sized bowling ball would accelerate faster toward the bigger Earth, right? There's more force in the bowling ball than there is the feather, so the bowling ball is going to win in that scenario.
But scaling everything up by 1,000,000 wouldn't change much. Yes, the gravitational field of that huge bowling ball would be 1,000,000 times bigger, but so would the gravitational field of Earth. So the proportions would be still the same and still negligible. So I get why you had the idea, but the problem would be still that it's not noticeable.
Bowling ball is going to win in that scenario. But in this scenario, you just assume that because there's so little force in the bowling ball and in the feather that it doesn't even matter? Or you think, like, what is actually being imagined in your mind to make you think this is normal, like this is how it should happen? Like you think the most mass, the most attraction, but then you're like, well, when it comes to the bowling ball and a feather dropped in NASA's vacuum falling at the same rate, that's how it should happen.
Again, that is what I meant with it is counterintuitive. But again, our experience isn't the gold standard for that is how reality has to be. We are still humans and experience the world around us by signals through our nerves and our brain kind of painting a picture about it. So there is the possibility that the world around us doesn't look anything like what we imagine it does, but we won't ever know because our experience is just based on our brain using all of these electric signals in our brain and painting a picture for us. So, but again, valid questions. I think he really thought about gravity, and yeah, I can respect that. So let's watch the next video.
All right, is acceleration the same for all objects? The acceleration of the object equals the gravitational acceleration. The mass, size, and shape of the object are not a factor in describing the motion of the object. So all objects, regardless of size or shape or weight, free fall with the same acceleration. They claim that it doesn't matter what mass there is, what mass you have that you're dropping toward the Earth, that's being accelerated toward the Earth, it's always going to accelerate at 9.8 meters per second squared, or whatever the inverse square law would dictate. So no objects of any other mass, varying mass, will have any other sort of additional force. But all matter in the universe has gravitational fields. They all have gravity. They all produce this accelerating phenomenon. So whenever you introduce masses that are varying in their size or mass, there should be a difference in the effect. We should see the bigger mass produce more force. We should see the bigger mass produce more acceleration, which is what force is. And we don't see that. All we see is objects of any mass accelerating at the exact same rate. And we can confirm this in a vacuum chamber, which you can check out on my video titled Gravity, because it addresses this issue. Well, it's highlighting it, pointing it out, letting you know that it's an issue.
So this is halfway there. Again, our objects we as humans can lift up have such a tiny gravitational field compared to Earth that we don't take them into account when calculating the gravitational pull, like the 9.8 meters per second square. But when you use, for example, a huge meteor that has, I don't know, multiple thousand tons of weight, then you would take that into account too, because that would actually change the acceleration rate, as far as I understand. Because then you have the gravitational pull of Earth and the gravitational pull of that meteor, and they interact with each other, and technically they should fall faster than the 9.8 meters per second square. But that only makes a noticeable or measurable difference when that other object is very massive. But we know that the gravitational pull on different objects is different because it is directly proportional to the mass of the object. For example, on Mars, the gravitational acceleration rate is 3.721 meters per second squared because Mars has a different mass. Mars is smaller. But I do understand that that's a weird thought to get used to when you're just learning about it, or when you're just starting to think about all of this, because there are many people that don't get me wrong, that has nothing to do with being a flat earther or not. It has to do with, am I interested in trying to understand those things or not? So the thought of heavier things experience a bigger gravitational pull on them, so they are heavier, but they don't fall faster than objects with a different mass. So I get that that is a weird thought, because intuitively you would say, yeah, when it's heavier it falls faster, but that's just not the case. But the pull of that objects onto Earth are so tiny that we can't notice a difference. Just imagine the Australian wildfires, that huge area of fire, and you would let fall a drop of water into it. Yes, technically that drop of water should be cooling down something, but it doesn't change the result. There's no measurable difference because it's just so little.
And they don't really have a reason why the matter wouldn't accelerate at different rates. They just claim that, well, all mass, regardless of its mass, is going to accelerate at the same rate. You know, it's literally how we were able to create measurements, you know, base all of our measurements from. If we didn't have this balanced or this fixed figure, then it would have made things pretty confusing, I think. You know, because objects would be accelerating, if they're accelerating different based on their mass, then it would throw things off a little bit. I mean, maybe you'd still be able to calculate it, but I don't think it would be the exact same. The object with more mass would produce more weight and more acceleration. So I don't know if there would be more weight because it's producing more acceleration, or what the deal would be there. But there would be some sort of discrepancy. It wouldn't be the same thing as it is now. So they do not account for other mass having any other force.
I'm not sure what he exactly means by that. If he thinks that all the mass throughout the universe will have 9.8 meters per second squared, because that's wrong, but I'm not sure if that's what he meant. So just in case, no, every other mass throughout the universe has a different gravitational pull depending on their mass, because a bigger mass creates a bigger dip in the fabric of space-time. And when it's a bigger dip, things around here fall faster in the middle, regardless of their weight. But technically you are right, the more mass the falling object has, it should increase the acceleration. But most of the time it's just so tiny that it doesn't matter. Yes, they take that into account, but in your prior video also you just googled the gravitational pull of Earth. Therefore, you only get results referring to Earth's gravitational pull. If you would Google it of any other known mass in the universe, you would get another result. But again, there's also the possibility of you calculating it. Just try and find a course on how to do it. You can actually do it yourself and try to understand it by doing different experiments, because you obviously have a very big interest in all of this and you want to understand it, and you are actually sitting there thinking about it, and that is a good thing. That is a good basis for what the possibilities can be in understanding all of it.
And they will sit you through a Cavendish experiment or a Cavendish lesson and tell you how matter is being attracted to other matter. And they can literally use one fixed mass or a couple fixed masses and then use all sorts of different masses that accelerate towards those fixed masses. And you will get a different freaking acceleration every single time. Every single time they change the masses around, you get a different acceleration rate. When you put objects in a vacuum here on Earth and drop them, the same exact acceleration rate, no matter how much you change the fucking masses.
Yes and no. So the Cavendish experiment was a very, very well thought out experiment. First of all, those masses won't compete with the gravitational pull of Earth because the gravitational pull pulls vertically down, like this. And the Cavendish experiment had it like this. There were the two lead balls, and they were acting on each other because this force is perpendicular to Earth's gravitational pull. Therefore, it won't interfere with the attraction between those two lead balls. Second of all, yes, you did get a different rate of attraction because those different masses of these lead balls will create a different force of attraction. It has nothing to do with the gravitational field of Earth. When you have those lead balls and you know their masses and you know the distance between them, when they attract each other, you can calculate with the rate and the time they're attracting each other with the weight, the mass they have. You can come up with a value of this acceleration of attraction per kilogram, for example. And that is what you can use and apply it onto Earth. That is how they did it. So the proportion between mass and acceleration are the same throughout the universe. But when you use different masses, you of course have different accelerations. But I think I get where your problems in all of this stem from.
Now, dropping objects in a vacuum on Earth is, well, a little bit better than the Cavendish experiment. It's the exact same thing as the Cavendish experiment. Only difference is there's no wires and there's no air resistance.
No. Cavendish is the more controlled experiment, again, because because it doesn't depend on Earth's gravitational pull. We know, or we knew before Cavendish probably, the acceleration of things falling down in a vacuum. Thanks to Cavendish, we know that rate is proportional to the masses. So the Cavendish experiment, although flat earthers oftentimes think very differently, the Cavendish experiment was to calculate the gravitational pull. Thanks to the results of that experiment, we could apply it onto Earth, and it matched what we knew beforehand and what we calculated because of the results of the Cavendish experiment. So it not only did prove that we were right about the gravitational pull with the acceleration rate, but also that there is a relation between the rate of acceleration and masses of objects, and that not only Earth has a gravitational field, but every object has. So the Cavendish experiment was incredibly important for modern science. And sadly, many flat earthers really underestimate the Cavendish experiment's effect on modern science.
What factors cause acceleration to vary at different locations? The distance between the centers of mass of two objects affects the gravitational force between them, so the force of gravity on an object is smaller at the equator compared to the poles. This effect alone causes the gravitational acceleration to be about 0.18% less at the equator than at the poles. So the poles are closer to the center of the Earth's mass than the equator, and so therefore they have more force than the equator. There's more force at the poles than at the equator, because it's closer to the center of mass. The only problem here is the equator is larger than, if you're standing on the equator, the point from you to the other side of the sphere, to the other, the other side of the equator, there's more mass there than if you're on the pole, to the, looking down to the other pole. There's less mass there. So you're saying you would be attracted, there's less gravity when there's more mass.
So that is pretty easily explained with the inverse square law. you were talking about in the beginning of the first video. Because the closer you get to the source of the force, the stronger it is. Because when you distribute the same force onto a bigger area, it decreases in proportion. It's the same with light. My softbox is lighter when I get closer to it. When I get further away, it gets dimmer. But it doesn't actually get dimmer, but the light it produces, the photons it produces, have to spread onto a bigger area. Therefore, per area, the photons I get decrease the further away I go. And it's actually the same thing with gravity. But you are right, on the poles there is technically less mass. But this less mass has a smaller effect than the closer you get to the center of mass. So again, the idea you have is valid, but the effects of those ideas aren't as big as you think.
You need contact to produce centrifugal force. So say if the object was sitting on Earth, was resting on Earth, was in contact with other mass on Earth, then it would produce a centrifugal force. But since there's no contact, no centrifugal force. But here we're saying reduces the apparent downward acceleration of falling objects. So the spin of the Earth reduces the acceleration of falling objects. So for at the equator, we set up a vacuum chamber, like NASA's vacuum. We drop a couple objects. They're going to accelerate at a less rate at other latitudes. How is that possible if the centrifugal force doesn't come into contact? I mean, it doesn't work until it comes into contact. That doesn't make any sense.
So that was one of those questions where I was sitting there for a minute like, actually, I think he has a point, because I never thought about it that deep, but I came to a conclusion. The atmosphere spins with Earth. You and I spin with Earth. Everything spins with Earth. So we have the same surface velocity than Earth. When we let something fall in a vacuum, so for one, this conserves the angular momentum when it's in free fall, because it spins, even though for us it falls down vertically, but it spins with Earth at the same velocity as Earth does. So the centrifugal force is still the same on that thing. So the centrifugal force is still the same on that object. So I get where the idea comes from, because I was sitting there for a minute and was like, But again, it is, as far as I could find, still the conservation of momentum, and that results in the effect of the apparent force of centrifugal. So most of the questions from flat earthers are actually really easily explained by conservation of momentum. How funny is that? And now let's watch his third part of gravity, and this will be the last part. This video is long enough, but that video of his is only 1 minute and 41 seconds long. So let's watch this, answer his questions, and then wrap up the video.
So if we think of two masses that are exactly the same, and we put them in an infinite void, they should attract to one another, correct? According to everyone's input on the matter. We'll just say that. But what's interesting is, and I was trying to find this video of this reduction in gravity experiment where they put a weight on a scale and put a weight above that, and it reduced the weight of the object on the scale, which you could measure with the scale. So I couldn't find that video, so I just thought about putting two objects in this infinite void and what would happen if with that concept in mind. And I thought, well, shouldn't the masses go toward one another if they have gravity? But also, if they have gravity, wouldn't they reduce the effect? So if they're exactly the same, they shouldn't go together, because they would have reduced whatever effect they had on each other.
That idea is at one part very impressive, because he accepts its validity, at least to a certain extent. He doesn't say, oh my god, that's so stupid. So yes, you can actually reduce the weight of an object when you put another heavy object above it. because there is attraction to it. So you can observe this reduction of weight or of gravity in that case with tides. The ocean has its weight because Earth's gravity pulls it onto the surface. But when you have the tides, there is the moon right above it, and the moon pulls it up towards it. So if you could weigh the ocean before the tide and after the tide, there would be a difference. So again, you are right, but for example, when you think it in the scale of you and me, we are incredibly light compared to an ocean. And the effect of the moon pulling on us is there, but again, incredibly tiny. So you are on the right track. When you have two objects with mass in an infinite void where there's no other gravity, yes, they fall onto each other. That is how stars and planets are created. When you have just two objects in that void, they just attract each other. It is possible that one thing can orbit the other thing, and slowly it would fall into them and they would crash onto each other. But they wouldn't negate their gravitational pull or their gravitational field. They would reinforce it at some point. What you confuse it with is when you have those two massive objects and one thing in the middle. When those massive objects would have the exact same mass, the exact same distance to the object in the middle, they would negate it. So there would probably be the one thing in the middle locked gravitationally in both directions. But two objects, they just pull onto each other. So I hope this could answer some of the questions. I think it was an interesting video also for me, because it's not that often that a flat earther makes an actual effort in understanding what is gravity, what does it mean, how does it work, and I have to give you credit for that. You actually tried. You actually tried to understand it, to get more information, and you had your own ideas on, okay, if that's a thing, then this should happen. And I think it's a great thing. I hope I could answer some of your questions. If you will see this video, if you are interested in talking on a live stream or in just me answering some other questions, please let me know, write a comment, email, whatever. I would greatly appreciate an interaction with you, because you seem to be more intellectually honest than some of your fellow flat earthers. And to everyone else who was watching this video, I hope you did like it. I hope you did learn something. If I got something wrong myself, which is absolutely possible, I'm not a scientist, please let me know down in the comments. Let me know what you think. And I hope I will see you next week in the next one. Thank you. Bye!